In this lesson, we're going to take a look at factorial notation. So first, we're going to consider what is a factorial and what exactly is meant by factorial notation. And then we're going to connect this to what we did in the last lesson and see how we can use factorials to compute permutations a little bit more easily. So first off, the definition of a factorial. The factorial of a number, and these numbers are always positive integers. Factorial of a positive integer or some number is that number multiplied by all of the integers that are less than that number and greater than 0. The symbol for factorial is a number followed by an exclamation mark. So n exclamation mark means n factorial. And again, n is just a positive integer. So n factorial is n times the number less than that, n minus 1, times number less than that, n minus 2, times so on and so on and so on, all the way down to 3 times 2 times 1. So it's a string of numbers multiplied together. So for instance, 8 factorial here would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we can punch this into our calculator using, most calculators have a factorial button, and it'll spit out the answer 40,320. 2 factorial will be all of the numbers starting with 2 times all of the numbers less than it but greater than 0, so 2 times 1, just 2. So the first term in this factorial is always this expression of this number that you see right before that exclamation mark. 1 factorial is 1 times, well, just 1. The only one that's a little bit weird is 0 factorial. It doesn't quite fit this description that I gave up above, but 0 factorial is just 1 as well. And we'll look at that in a little bit. So how do factorials help us compute permutations? Well, from last lesson, we know that if we're doing this permutation 7, 4, we know that this is 7 times 6 times 5 times 4. We have 7 things that we can choose from for the first item. And this number 4 here tells us how many places we have. 1, 2, 3, 4. How can we relate this to a factorial? Well, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Notice that these two things, these two expressions that I've written here are the same up to this point right here. Now this part that makes them different is 3 times 2 times 1, or 3 factorial. So we can make this expression, P74 here, it is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1 if we divide out the 3 times 2 times 1, i.e. we want these things here, top and bottom, to cancel out, right? But let's not cancel them out right yet. Put them back in here. So what do we have on in the numerator of this expression? Well, we've got 7 times 6 times 5 times 4 and so on is 7 factorial. What do we have on the bottom? We have 3 factorial. So this permutation is equal to 7 factorial divided by 3 factorial. Now, how does that relate to these numbers that we have here that we were given at the beginning? 7 factorial, 7 goes right up in the numerator, and this 4 here is 7 minus 4 down in the denominator, gives us our 3 factorial. Permutation 7, 4 here is 7 factorial divided by 7 minus 4 factorial. Or in general, we're doing a permutation with n and r of r elements pulled from n total elements. The formula is going to be n factorial divided by n minus r factorial. So let's look at a couple of examples of applying this formula here. First permutation we have, 9(2) is going to be, the 9 goes up in our numerator, 9 factorial. And down in our denominator, we're going to have 9 minus 2 factorial. So this can help us evaluate this. 9 factorial over 7 factorial. We know that what we have up in the numerator is 9 times 8 times 7 times 6 times ... What do we have down in the denominator? We've got 7 times 6 times 12, ... and so on and so on. All of these terms, we can cancel out terms in the denominator and the numerator. 7 cancels with 7, the 6 cancels with the 6, and because each of these chains of multiplication keeps going all the way down to 3 times 2 times 1, all of this remaining stuff will cancel out as well. So this permutation here is actually just equal to 9 times 8, or 72. So we can apply this to do a little bit of algebra, working with expressions in these factorial notations. So if I've got something like number 2 here, 12 times 11 factorial, I know that that is 12 times, well, what's 11 factorial? 11 times 10 times 9 times 8 times all the way so on and so on. But if I look at this chain of numbers multiplied together, I've got 12 times 11 times 10 times 9 times 8, or 12 factorial. And we can do this even when we don't have a specific number in there. N times n minus 1 factorial. Well, let's see, what's this going to be? We've got n out front times, what's n minus 1 factorial? Well, the first term in the factorial, or that chain of things multiplied together, is going to be whatever we see there in front of that exclamation mark. So our first term is going to be n minus 1. And each successive term is one smaller than the one we start with. So we go from n minus 1 to n minus 2 to n minus 3, and so on and so on and so on, all the way down to 3 times 2 times 1. So now we have n times n minus 1 times n minus 2. So again, we have this string of things multiplied, string of terms all multiplied together. Each successive one is one smaller than the one in front of it. The first term is n, so we can write this as n factorial. And that's the same as question number 2 here if n is equal to 12. We can get a little bit trickier with these things. 72 times 7 factorial. Well, think about what 72 is. It's actually 9 times 8. So we have 9 times 8 times, what's 7 factorial? 7 times 6 times 5 times, you get the idea here. So altogether this is going to be 9 factorial. Other times we're going to have expressions involving factorials that are divided by each other. So we've got n plus 1 factorial divided by n minus 1 factorial. I think a good way to start doing these at the beginning is to just start by writing the first few terms of each of our factorials. So n plus 1 factorial, the first term is going to be what we see in those brackets, n plus 1. Times, what do we get when we subtract 1 from n plus 1? Well, we just get n, and then n minus 1, then n minus 2, and so on and so on. What are we going to have in the denominator? First term is going to be the n minus 1 that we see there, times n minus 2, times, and so on and so on and so on. Now, let's look for terms we can cancel in the numerator and the denominator. N minus 1 and n minus 1, n minus 2 and n minus 2, and in fact, all of these terms, successive terms, are going to cancel each other out from here all the way along down to there. So we're going to be left with just the n plus 1 and the n minus 1 that we have up here in our numerator. And that sort of thing we can just expand n squared plus just n, using our good old-fashioned distributive property, multiplying each of those terms by n. So a little bit of an application of this, putting some of these things together. you might be given a question like this. Solve for n, where n minus 1 factorial divided by n minus 3 factorial is equal to 72. And let's start doing just what we did before. We will expand a few terms of these factorials that we have in our numerator and in our denominator. So in the numerator we have n minus 1 factorial, so we'll start with n minus 1 times n minus 2 times n minus 3 times, I've been putting those times in there, so I should take that one out, n minus 4 times, etc., etc., etc. Down in our denominator, we're going to have the n minus 3 that we see times n minus 4 times, well, it goes on from there. All of this is going to be equal to 72. Now let's look for terms that are going to cancel out in our numerator and our denominator. N minus 3 and n minus 3, n minus 4 and n minus 4, and everything beyond those terms is going to cancel out as well. So we're left with n minus 1 times n minus 2 equals 72. And we want to solve this thing for n. So remember what solving means. We want to get n all by itself on one side of this equation and a single number on the other side. Well, how can we do this? Let's start by expanding what we have on the left-hand side here. So using our good old FOIL rule, n minus 1 times n minus 2, we're going to get n squared minus 1n minus 2n plus 2 equals 72, which when we collect our like terms is n squared minus 3n plus 2 equals 72. How can we solve this? Well, when we see this term n squared, we know that what we're dealing with is a quadratic. So we're going to want to solve this by factoring. But first we need to move everything onto one side of our equation. So let's subtract 72 from both sides here to get n squared minus 3n minus 70 equals 0. And then let's factor this expression. So how do we factor this trinomial? We know we're going to have two factors. We need an n here and an n here because when we expand that out, that's what's going to give us our n squared. We're looking for two numbers that multiply to negative 70, add to negative 3. So those numbers are going to be negative 10 and positive 7. So this is telling us that our solutions here are n equals negative 7 and n equals positive 10. Are both of these good solutions? To answer that question, we have to think about what would happen if we took these values for n and subbed them in to our original equation up here. So originally we had n minus 1 factorial and n minus 3 factorial. If we try subbing in n equals negative 7 to, let's say, n minus 1 factorial, just imagine subbing that in, we get negative 7 minus 1 factorial, or negative 8 factorial. And this doesn't make any sense, because we said at the very beginning that when we were doing factorials, we only wanted to use positive integers here. So because this makes no sense, we just ignore this solution, and we only keep the positive one. So n is just equal to positive 10.